Good morning, everyone. Today is February 3rd, 2018, and this is the Chappell National Philosophy Society Science Chat. Brought to you by the Chappell National Philosophy Society, and we invite you to explore our website and to join us. We have lots to discuss on our wiki and our forum.
Franklin, your mic is terrible.
Is it?
I can't hear you. Oh, that was good.
Well, I was using just a second. Backwards, just a second.
No, coming in and out in a hum.
Second. I've got a fan back here. Okay, is that better if I don't use my headphones?
If you don't use your headphones, it sounds good.
All right, well, we're going to have to go with that. Sometimes we get echoes, so if you're not speaking, please keep yourself on mute. But my new headphones don't seem to check that out. Okay, so that's the introduction with CNPS. And let's see here. I'm going to mute whoever's on the phone there since you're making some noise. So today's topic is going to be, let's see here, let me bring up my paper here. We're going to be talking about specifically how the protons are attached with neutrons, or what their purpose is, and like what's a proton, what's a neutron, how are atoms actually configured. So let's get started on that. So as I was mentioning as our introduction, is like we know that there are protons in the atom. And the question is how do they stick together? The conventional picture of the atom is that we have a compact nucleus which basically only contains protons and neutrons. So what the question is, why is it that those protons just don't fly apart? Because of the incredible repelling force of the neutrons at that distance. I mean, basically they calculated what the repelling force is, and it's like, you know, like millions of pounds of force forcing the protons apart. And what is commonly said is that it is the strong force, which is a mysterious force, which is very powerful at very short distances, but has absolutely no force outside of, say, the atomic nucleus dimension. So, but the question is, if it's the strong force which is holding the nucleus together, then what exactly is the role of the neutrons? I mean, is it the strong force that's holding it together? Is it the role of the neutrons isn't even clear in this picture. I mean, does strong force come from the neutrons? You know, why is it so short-ranged? And there's just a lot of questions about
Franklin, I thought that the strong force is working within the hadrons. So within the proton and or within the neutron, and not between the proton and the neutron.
So is it working within the neutron, or is it working between the neutrons and the protons? I mean, what is the mainstream picture that they're trying to paint?
I think the mainstream is that the strong force works between quarks, and the quarks are forming the protons, and quarks are forming the neutrons.
Well, that might explain how neutrons are put together, but that doesn't explain why is it the strong force is holding those protons together.
I know. I think, yeah, that they have some explanation for that, but in first stage, the quarks are holding together by the strong force. That's what quantum chromodynamics is about.
Yeah, that just seem to be a lot of questions here. But the neutrons do seem to play an important role. I mean, there are no atoms that have like no neutrons, for example. For example, with helium, I mean, you can have a helium-3, which has one neutron, but there's no such thing as a helium-2, where there are just, two protons. That just doesn't happen. And there always seems to be a ratio of at least 1-to-1 protons to neutrons in stable nuclei. So they do seem to be very important, which kind of leads you to the idea that the neutrons are there to somehow glue the protons together. They do seem to be a necessary component, and they're a solid part of the atom. They're not easily ionized. I mean, the only thing, if you excite an atom, the only things that come off the atom are electrons, normally, right? The electrons are loosely bound, but whatever's going on with the protons and the neutrons, those are tightly bound together. So, maybe that kind of goes with the mainstream picture that there's this nucleus that has only the protons and the neutrons in it, and that only the surrounding electrons can be ionized. But still, it doesn't answer the question of, how does a neutron glue protons together? So let's explore that idea. Now, I would assert that, as far as mainstream concerned, I would assert that almost everything that we think we know about the atomic nucleus or atom structure is, in fact, wrong. I mean, basically, not a little bit wrong, but like flat Earth wrong. I mean, just really completely almost backwards. So the first thing I'll have to ask you to forget about is this concept of a nucleus. That is that there's this tiny ball sitting in the middle of the atom, and I'm sure you've all heard about this, that, if the size of the nucleus was like the size of a golf ball, the actual size of the atom would be like the size of a city or maybe even a state. It's just insanely small. And that this nucleus only contains the protons and the neutrons. Now, I don't know about you, but that picture never, ever made any sense to me. I mean, if you go on Quora, people are always constantly asking questions like, well, if the atom is like 99.99% empty, then how come I just can't stick my hand through the wall? Because if the atomic matter was really that sparse, 99.99% nothing, then one would logically expect that solids would be able to pass right through each other. I mean, it's like it's so sparse, right? And people can't really come up with really good answers other than, oh, it's the field, it's but basically they're just making stuff up. And if you think that the neutrons somehow glue together that compact protons,
in your opinion, they're making stuff up. It's based on facts, experiments. That's what science is. Science does experiments, obtains empirical facts, and then bases theories on empirical facts. Well, at least that's what they claim they do. But you're saying the empirical facts are wrong. So that means, I don't know where that leaves us. If you claim all the empirical facts are incorrect, which is your thesis, then we have no science because we have no empirical facts.
Yeah, we're having a hard time here. That's you, Harry?
Yes, correct. So your fundamental claim is that the empirical facts upon which the science of the nucleus is based is wrong. Okay, so there's no science there at all because there's no empirical facts. So yeah,
So
sure,
the
you can
empirical
deny
facts
the
are the
empirical
empirical
facts.
facts.
Yeah, you're
For
denying the
example,
empirical facts. That's what you're doing.
the empirical facts are, for example, the Rutherford scattering data. Those are empirical facts. But what is not an empirical fact is the conclusion that the nucleus is as small as they estimate it to be. That is not an empirical fact.
So what's your basis for claiming that?
What is happening?
I got no audio here.
I think we lost Franklin.
Yeah, I can hear everybody but Franklin.
Bill Lucas, are you out there?
Yes, I'm here. Can you hear me?
Yeah, what do you think about this thesis that the Rutherford experiments are wrong?
Well, I think that they are fairly accurate for size. However, the part about the nucleus not consisting of neutrons and protons is well established by the NIST data. They've measured the mass of the nuclear isotopes, the 3,500 of them, to 8 significant figures, and now there's no evidence for the strong interaction or the weak interaction in the nucleus, and there's no evidence for neutrons. And so
That's certainly an interesting viewpoint.
So something else is there besides just protons, but it's not. It's electromagnetic. It's not strong interaction or weak interaction. The model that is promoting is an electromagnetic model, and so it would be compatible with that data. But you've got to be able to predict the data to 8 significant figures.
Okay, I'm back. I think the man's trying to shut me down. Hopefully we won't have any more interruptions like that. Okay. So I was talking about all the things that are kind of hard to believe about the atomic model. And I would suggest that we need to have a new way to describe this so that it actually makes sense without so many questions. So let's start. So I suggest that you clear your mind about all your preconceived notions and just start anew. So let's try and figure out what a proton is. Okay, so a proton has a singular positive charge, and there appear to be 3 things that are inside that proton. So we can tell that by scattering. So there are these 3 things, and mainstream it claims that these things are fractionally charged quarks. And they've got like 2/3 charge and 1/3 charge, and they all add up to produce the singular positive charge. However, quarks have never, ever been seen in isolation. We have never, ever seen fractionally charged anythings at any time. And a lot of people have spent a lot of time looking for these things because there's no theoretical reason why they shouldn't exist. So, we should have seen these in our particle accelerators from the get-go. There should have been like, oh yeah, there's the 1/3 charged particle. But we never, ever, ever, ever see anything that looks like it has a charge of a quark. But if it isn't a quark, then what is it? So the only other particles that we know about that have charge are positrons and electrons. So we know those exist. Those definitely show up all over the place in our accelerator experiments. There's no doubt that positrons and electrons exist. So if those are our building blocks, then what could a proton be made out of? And I say, using simple algebra, that a proton has to be, 2 positrons and 1 electron. That would be the simplest possible thing it could be. I mean, I suppose it could be 3 positrons and 2 electrons, just any combination that would allow it to have a remaining +1 charge. But since experiments say that there are 3 things in the proton, then logically, it could be 2 positrons and 1 electron. And so that would be my claim, that, all this quark theory, it's just a bunch of hooey. It's made up, it's mathematical, has very little experimental evidence behind it. So that is what I would claim a proton is. So that brings up the question of what is a neutron? So we believe that neutrons, we are able to detect these things independently. We can create neutron beams. They appear to have no charge. And it would seem that the simplest possible combination of positrons and electrons you could have to produce that would be 1 positron and 1 electron. So that is basically what I claim a neutron is. It's 1 positron glued to 1 electron. But of course, the immediate objection to this would be from the mainstream is that, well, those 2 things annihilate, right? There's no way a neutron can be made out of positron and electron because it would immediately annihilate, turn into gamma rays, and it would disappear, right? And that is yet another preconception that I would ask that you let go of. Now, I know it's all popular and everything to say that E = mc squared. Mass converts into energy, and that's what we're seeing in the annihilation. But I would ask you to let go of that concept and instead think of when a positron and electron come together. So for example, I have this red block, that's a positron. I have a black block, that's an electron. I would ask you to think that, well, by Coulomb's law, they would attract and they stick together, right? Now this is a neutrally charged particle. It's if it produced this, would be very hard to detect.
Franklin, I got a question for you.
Yes.
Well, actually, I have a question for the group. Is anybody on here, I certainly haven't, has anybody in this conference group done any actual experiments regarding elementary particles other than Bill Lucas? Is anybody familiar with doing these experiments other than Bill Lucas? So it looks like
I did. Sorry, I did. I worked with image intensifiers, X-ray image intensifiers, and I also worked with electron optical lenses. They work with electrons or protons or charged particles. So most of these charged particles were elementary particles. And as soon as you bring together a particle that has opposite charges, then they bind and combine into something neutral. There is one thing that keeps things apart, and that's known as the Pauli principle. The Pauli principle takes care that things that have equal properties cannot take each other's places. And that is holding most material apart from each other. That's why a chair underneath you doesn't collapse.
I think that would be a very basic spatial property that objects cannot exist in the exact same piece of space at the same time. That there's always some sort of displacement. But in any case, I'm personally not able to.
That explains your question about why a hand can't pass through an atom.
Yeah, that's the concept of solidity. But if the thing is that this thing is 99.9% like air, that means the solid parts where the particles cannot pass through each other, there's a lot of space for that. So you don't have to have like two protons in exactly the same bit of space. And if there's that much room for them to move through, then then they should be able to just pass right by each other. So that's assuming that protons
understand why. I sort of understand that this question that you raise about this has been an issue in the philosophy of science.
Yeah, and I think it's an important question because I actually fundamentally don't believe it's true. I don't believe that the atom is 99.99% empty space. I believe that the atom actually completely fills the observed diameter of the atom. Completely, solidly.
Well, it depends on what you mean by empty space. I mean, you're using the term empty space. You've got a bunch of hidden assumptions in your words that you're using, and then you use a certain assumptions in your words to produce a contradiction, which really is based on your assumption about what words mean that you're using, and those assumptions may not necessarily be true. You're assuming empty space has a particular meaning in the way you use it. It's not empty, it's got fields in there.
We always have those kinds of problems. So we do need to try and be clear. And we make things clear by asking questions and getting answers. So,
well, but an atom would appear to be full of fields, right? I mean, there's a lot of stuff going on there as far as fields are concerned. So, yeah, it could be empty space as far as matter is concerned, yet full of fields.
Yes, that would be correct. It could totally be that way.
So it's not empty. So the word empty is kind of a misdirection word.
Yeah, that could be misdirecting. You'd probably be, to be precise, to say empty of normal visible matter, protons, electrons, neutrons. But could be filled with something else. Could be completely occupied with matter.
Well, are you proposing that there's ether in there? Is that what you're going to propose?
Well, that's a basic part of my theory. Although we're not really discussing ether in this particular thing, but we may get to that. But we're talking about the neutrons, and so getting back to what neutrons are, I believe that they are just
Well, don't you think before you do that, you ought to basically talk about what the evidence is that leads scientists to believe that neutrons exist?
Well, we believe.
Supposedly, this guy Chadwick discovered the neutron.
Well, I already discussed that. We can identify individual neutrons. We can create beams out of them. I think Bill Lucas has pointed out very correctly that real particles exist if you can form a unique beam out of them. I don't think anyone could say that neutrons do not exist if we couldn't, well, then what is this a beam of, right?
Okay, so neutrons can be identified as objects that exist outside of atoms. And
Yeah,
and their properties can be described in certain ways. You can manipulate them and do things with them. And presumably, I don't know how they're measured, their properties are measured, whether they're inferred from their properties inside of atoms or they can be measured outside of atoms or not.
well, they are inferred inside of atoms because they add to the mass of an atom. So we can definitely measure the masses of atoms. And we are able to do things like observe atomic decay and see neutrons be ejected, and we can then remeasure the mass and see that something came out of the atom, and it wasn't a proton and it wasn't an electron. And the thing that's losing these things, we detect neutrons. So those are all kinds of the evidence for this thing that we call a neutron.
All right, let me stop you here. Bill Lucas said that earlier when you were kind of messing around with your equipment there and we sort of had an interruption, Bill Lucas sort of made the comment that he didn't think neutrons existed in atoms. So I'd sort of like for him to elaborate on that a bit because he has a kind of a different opinion about it.
Yeah, we will definitely get into that. And once again, as you point out, it's kind of a definitional kind of wordplay kind of thing, because form beams out of, they're called neutrons. But it is kind of a presumption that those things that we observe in that beam are really exactly the same thing that we see inside of atoms. I mean, because we can't look at a neutron while it's actually basically inside of an atom. That's
okay. So the first thing that we have to do is we have to sort of decide what empirical evidence permits the identification of the existence of something called a neutron and that it exists inside of atoms. That seems to be your first point of contention. Am I not right on that?
Well, I wouldn't say that's the first point of contention because we do have a lot of, we can point out the experimental evidence. But if you let me go on, I'll try and explain at least how I see this fitting in the picture. But you just have to get first of all, the point that, a neutron is a composite particle made out of positrons and electrons, as well as a proton is a composite particle made out of two positrons and electrons, and things like quarks don't exist.
Well, you're jumping into your assumptions and your theory without really telling us what the experimental evidence is.
Well, I mean, I have given you what the experimental evidence, some from the mainstream, like, we've already discussed, why we think neutrons exist. And I think that's the basic evidence that we have. So,
well, I'm not real familiar with that. And that's kind of why I want to hear from Bill. But anyway, go on. All right. I'm real skeptical of this hypothesis, that you're asserting. I mean, you're making this hypothesis that neutrons consist of a positron and an electron in some kind of combination. Is that not correct?
That is absolutely correct. So, and as a scientific theory,
that introduces us to the idea that there's some kind of a, we're dealing with units, and so we can take a positron as a unit of something and an electron as a unit something and put them together and get something else, right? That's what you're saying. Absolutely.
That is absolutely correct. And right. I want you to be skeptical because, this is nothing experimentally proven, as you might point out. This is just a hypothesis. And hypotheses are put forward to try and explain experimental results. So we have the experimental results that we can see things like neutrons. They add weight and mass to atoms. They appear to be necessary to form an atom. And so the initial hypothesis is that the neutrons are gluing together the protons. So that's how the story got to this point. So the question is, how could you glue protons together? Okay, so I've asserted that a proton is a positron plus an electron plus a positron. So if you had two of those things, how would you glue them together? So I would propose that you could do that by just putting an electron between them, right? Because opposite charges attract, and the proton would likely be in a chain, and if you just put an electron between them, that'd do it, right? Because it'd just be an array of opposite charges. So in that way, it's not that tough to glue two protons together. All you do is just put a negative charge between them, and they will immediately glop together, and they'd be perfectly happy together. I mean, you could make the Coulomb law calculations, and it would be trivial to show that, yeah, that would join together, and because it's all equally charged, it would not repel each other, and it would be stable. However, atoms are not long chains, right? You could imagine you could chain together as many protons together as you want with a bunch of electrons, and you get this really long stringy atom. But I don't think atoms are long chains. They appear to be spherically symmetrical, and so that's not the right picture. So I think you could fix this, though, if you could make loops out of them. And I think that you could imagine that if you stuck another electron and you just bent the chain around to the other side, that you could create this chain of electron, proton kind of thing. And that too would be stable. So that is what I'm suggesting, that if you add another electron, this will allow the protons to form a loop. And so I have a little picture here. It's kind of crude, but the large black circles you see here on the upper left and lower right represent the electron glue as a negative charge. And the protons are shown as being made up of two smaller red and one black circle. And you'll notice I've drawn the proton to be about the same size as the electron. And the reason why I do that is because size-wise, the most important thing about a particle is its charge. And the charge radius of a proton is exactly the same as the charge radius of an electron. So by charge, and this is really the only thing that I think that subatomic particles really have to interact with, or at least that's the most important or the first thing that they interact with, is their charge radius. So a proton really should be considered the same size as an electron, even though a proton consists of three things, an electron is only one thing. So that's why I've drawn it this way. But you can see that this is one potential way for protons to be glued together. Now, but an electron is not what we would call a neutron, right? Atoms are not glued together by electrons. There is still this, because if they were, we would definitely see that the mass would be different. There is something definitely in there other than just two electrons gluing together two protons. So what is a neutron then? So we have this electron that's kind of unpaired. And so I would say that those electrons are unbalanced. And the only way you can make that balanced is to get another positron and mate it with that electron that's gluing the protons together. So now, once you
I'm having trouble connecting to the internet. Take a look at...
Be quiet, Alexa. Okay. Let's see here. We were talking to you, Alexa. Okay. So once you have an electron and you have a positron, then you have what I would say are the components of a neutron. So this is actually what the neutron is that it's just another positron associated with the electron, which is acting as the glue for the protons. But then we have this problem that we've got these two extra positrons, which would not lead to a neutrally balanced atom. So those two positrons will attract two more electrons to the atom just to balance out the charge. But they're really not, tightly attached to anything. So this is why these electrons can be ionized off the atom very easily. But the components which are involved with the neutron, which is actually the electron plus the positron, those, and I'm not exactly sure what the nature of how the geometrical bond works, but those cannot be easily ionized off the atom. That there is some kind of binding. I believe it's probably a geometric argument that keeps those components in place. So if I describe this as another layer of the atom, it would look like this other picture that I have, where we have basically alternating positron and electron charges, and these two layers stack on top of each other to form a complete atom. But if we add it up, what do we have? So between those two layers, we have 2 protons, 2 neutrons, and 2 electrons. And that, curiously, adds up to a helium atom. And if you look at it, basically only the opposite sides are touching. And because only opposite charges are touching, that makes it stable. And it also has the correct property that it has 2 loosely bound electrons that can be ionized without disturbing the proton bond. So everything that bonds a proton together is still there, even if you remove the 2 electrons. Another important aspect that we need to preserve. So what does this look like in 3D? So here I have modeled in Lego what a helium atom would look like. So on the top, I have identified in red bricks as the protons, and directly beneath that would be the free electrons. And on the right hand and the left hand side, you can see there's a matched positive and negative charge. And that is making up what we currently recognize as the neutron. And like I said, the neutron is merely a positron and an electron, kind of, not as tightly bound as the 2 positrons and electrons in a proton. I mean, there is some tight binding going on in that particle. The neutron, probably similar, but not so much. So I have built various different models to represent this. And this is my Velcro model. So this would be a model of the helium nucleus. And this is just showing the checkerboard positive and negative charges. And, if you calculate the Coulomb forces on this object with, this pattern of charges, you would find that this produces the strongest bond possible, with it being in this cube. The cube is a very, very strong, you could say that's like the lowest energy format, and any set of charges will actually try and get into this format as a helium nucleus. But that might be a little bit confusing. So I have this different model here which shows in white where the neutrons would be, right? So this would actually be the part that has the free proton and the free electron. And then these parts would be what we consider the neutrons, right? And you can see that the neutrons take the same amount of space as the proton and the electron. And I think that may help explain, why is it that the neutron is counted as massive as proton, right? Because we think that, the I think the neutron is what, like slightly more massive than the proton. Although I have a little bit of problems with that. But from a geometrical standpoint, you might see that, well, if mass kind of depends on like the atom's, quote unquote volume, that the neutron adds as much volume as the proton does. Okay, so let's go on.
Can I interrupt for a moment?
Sure.
Did you ever look at the residual strong nuclear force that's thought to be coupling neutrons and protons? And there is a paragraph on it on a webpage about the nuclear force, and I put the link to it in the chat box. If you click it on, there you see a picture that looks somewhat better than what you propose in your lecture.
Mm-hmm. Well, let's take a look at that. Quick look at that here.
I can make a comment. The NIST has measured the mass of the nuclear isotopes, 3,500 of them, to 8 significant figures. And that when the strong interaction and the weak interaction forces were invented, we were only measuring the mass of the nuclear isotopes to 4 significant figures. And so the data was compatible with the idea of the strong interaction and the weak interaction. But now that we've measured it to 8, there is no data left that would allow the strong interaction or the weak interaction to occur in nuclear isotopes. And the data to 8 significant figures only supports the electromagnetic force, or 1 over r² force. The strong interaction and the weak interaction have a 1 over r³ and 1 over r⁵ dependence. And so the data would be significantly different to 8 significant figures if those existed. But since they don't, we now find that the nuclear model, that the politically correct nuclear model, the data no longer supports it. And not only that, you do not see nuclear isotopes decay and neutrons come out of the nucleus. We don't see that. And we have 3,500 nuclear isotopes, most of which are radioactive and decay, and we don't see that. We should see that if they're real neutrons so there's something else that holds the nucleus together. And what Franklin has suggested is that there are electromagnetic particles that do it. And so that's his approach that would be compatible with this data. But the other problem is you now have got to produce data that's been measured to 8 significant figures. And that's a problem. So for instance, if I want to know what the mass of a proton is, if it's made of positrons and electrons, I know what the mass of an electron is, and I know what the mass of a positron is, and I know what the mass of a proton is, and the proton is not equal to the sum of the 2 masses, the particles that make it up. So how do you explain that kind of thing? And also you have a spin. The positron has a spin, the electron has a spin, and the proton has a spin. And when we measure the spin, the proton has the same spin as an electron or a positron. But we're adding 2 together, and 2 together should, a spin 1/2 should be equal either spin 0 or spin 1. And we're getting spin 1/2 again. So that's a question. And then there's the magnetic moment. Each of those particles has a magnetic moment. The electron, the positron, and the proton, when we measure them. And the magnetic moment of the proton is not equal to the combination, the sum of the magnetic moment of the electron and the positron. So there are a lot of details that need to be accounted for in some way.
Yes, there's definitely a lot of details, and I can address every one of those points. But you are correct that that these are questions to be answered, but it doesn't necessarily take away from the initial concepts. That because we have those things do need to be explained, but they are not necessarily related to the logic of assembling atomic structure. But I will try and get to that. But
well, I'd like to interrupt here for a second, if I could, and ask Bill some questions. Do you mind if I ask Bill some questions?
Yeah, why don't you go ahead, ask Bill some questions.
Bill, my question sort of relates to what you're saying. Kind of, I guess I'm a little bit confused by it. Let's just use the word. I'm looking for clarification. But here's my question. I think this goes to the methodology that we're talking about, which is that if you have a particle that you can identify it, that is a particle that has come out of an atom through these accelerator measurements. And my question is, the whole idea of what an elementary particle is, as I understand it, it's something that's measured in a particle accelerator experiment. So, for instance, we shoot an object at an atom, and then a bunch of stuff comes out of it, okay, that is measured, in the measuring apparatus of the machine. And the assumption is that the particles that came out were inside the atom to begin with. Is that not really what the assumption is? And that seems to me like that's like, taking what comes out after you've smashed it up and saying that we're going to pack those particles back into the atom and say they exist inside of the atom. Isn't that fundamentally where this notion of neutrons being inside an atom comes from?
Maybe some people at some time in history had those ideas, but the in the current theories that we have that try to explain this type of phenomena, you have certain properties of elementary particles that get preserved when you do a reaction. Like I've worked with pionic atoms where the pion replaced an electron and went inside the nucleus and allowed you to probe what was inside the nucleus. And since the pion can interact with protons, neutrons, etc., you get to see those interactions up close. And you get to see that there are structures inside the nucleus. Just as Franklin would have structures in his nucleus. And you get to be able to see some properties of that structure. And but when you make pions, for instance, you take protons and bang them into something like carbon atom, which would be primarily the nucleus, and the proton would be hitting that nucleus, and then all kinds of particles come out. And then you use electromagnetic fields to sort them out and to form beams of those particles. So that's how we get a beam of pions and muons and kaons, and which come in different charge states. And so we have all these elementary particles that we can make. We can make a beam, and the particle may be decaying over time, but it lives long enough to perform experiments. So you can measure its properties, and you can see how it decays, and you can do a lot of different things with it. You can also see how it reacts with other particles if you bang them into one another. And so the various theories that we have of elementary particles and atoms and nuclei depend on that data. And currently the problem is that all the atomic data is not explained by any one of the atomic models. Only half of the data is explained. And then a lot of the nuclear data is not explained by the politically correct theory of the nucleus, what we call the shell model, quantum shell model. And So we have a second model we use to work with the nucleus, and that is the liquid drop model of the nucleus. And between the two of them, they sort of cover most of the properties of the nucleus, but they cannot predict what are known as the islands of nuclear stability. And that is, if you were to make a graph or a plot of all the observed nuclear isotopes, you'll find there are some islands of nuclear stability that are not connected to the other nuclei. And there's holes. There's a place where there's a sea where no nuclear isotopes observed, and that's a problem that the theories of the nucleus cannot explain. Why there are isolated islands of nuclear stability, and they don't all fall in one chart. And it's either stable or it's not, and the stable ones are all connected. Well, that's what they thought it would be when they first started, but now that we've gotten to the heavier and heavier nuclei, we see there are islands of nuclear stability, and so that needs to be explained by any theory.
Bill, can I interrupt you for a minute here? I got another question.
Okay.
So here's my question. My question is this. When we fire whatever it is, particle at material which has a nuclei which we think we understand, they really are only measuring what's coming out. They can't can they actually see, or do they think they see what's inside the nucleus? Or is what's inside the nucleus based only on theory? And in other words, what I'm asking is, are there any measurements, or do they actually measure what's inside? Can they see inside the nucleus, or are they merely inferring what's inside the nucleus based on the theories? You understand what I'm saying?
Yeah, they don't claim that in these experiments. They don't claim that all these particles that they see coming out of, let's say I bang a proton into some carbon, a block of carbon. They don't claim that those particles coming out that they see inside the nuclei. They just claim that there was a reaction between the high energy proton and the protons in the nucleus that they hit of the carbon nucleus, and that they are producing all these myriad of particles depending upon the energy of the proton when it was coming in to hit. In other words, if they have low energy protons, they're not going to get all these elementary particles. If they use high energy protons, then they will. And of course, they will break up the carbon atom or nuclei to some extent, and they'll form a few other types of nuclei. But most of the time, they think that the energy is being converted into matter. But all the characteristics of the matter have to be conserved. So not only are you conserving energy, but you're conserving all the quantities that we consider quantum quantities, like spin, charge, and various other quantum numbers that are in.
Now, I understand that, Bill. Now, here's my question. If you're shooting these things, they can't actually say, oh, we hit a neutron. They can't actually say what's in that nucleus. They can only infer what's in there based on the theory. Is that correct?
They don't use this type of experiment to see what's inside the nucleus. They use this experiment to make elementary particles.
Right. So how do we think we know what's inside the nucleus?
Well, may I just interrupt to say that we do observe radioactivity in a lot of elements, and we do watch, or we think we see, even without externally bombarding them, we do see electrons that seem to squirt out of them, and we do see alpha particles that are thrown out of them. We see cosmic rays. I mean, we see
gamma rays that are kind of thrown out of them. So I just insert that we don't always have to depend solely on hitting a atom with other particles to try to infer what is inside of them.
Yes, that's not the way we do it, but if you just look at what comes out of nuclear isotopes, many of which are radioactive, which means they decay, we see protons coming out, we see alpha particles, we see gamma rays, we see electrons and positrons, but we don't see any neutrons coming out. But the reason that they were thought to be in there is we have seen neutrons from these other experiments where we're bombarding things. We know that the neutron exists as an elementary particle, but we don't know for sure if it's inside. But it turns out that there's a binding energy to the neutron, and it's we know it's like 8 MeV, and when we can measure the mass of nuclear isotopes to 8 significant figures, that's like at the 4th significant, third or 5th significant figure in what we're measuring, and we see that there's no, in the decay of these nuclear isotopes, there's not enough energy to conserve energy and have a neutron inside there that is disappearing when it decays. And so that binding energy is missing. We can't account for it anywhere. We don't know where it is. And if we believe in the concept of energy concentration, neutrons in the nucleus.
I'm sorry, but the last part kind of went down, Bill. Could you repeat that?
Okay. We only have to measure the mass of nuclear isotopes to 5 significant figures to discredit the idea, the notion that there are neutrons inside of nuclear isotopes.
Okay, so what you're saying, as I understand what you're saying, is that what the idea that neutrons are inside of a nucleus is more of a theory than an actually empirically demonstrated fact.
Right. It is falsified by the data. It cannot predict the data for 13,500 nuclear isotopes. We don't have a single one of those isotopes that gives off neutrons. Not a single one. And so why do we think they're in the nucleus? We only think they're in the nucleus because we have need a mechanism to hold the protons together. Now, another mechanism would be we have a second elementary particle or something that's of an opposite charge that holds the different particles in the nucleus, the protons together in the nucleus. And the nuclear isotope data at 8 significant figures shows that the only force acting in the nucleus is a 1 over r squared force. And since neither the strong interaction or the weak interaction is a 1 over r squared force, they are not there.
Well, Bill, I think I thought the way I understood it, we detect neutrons is as a result of a nuclear reaction of decay. We detect neutrons not directly through like the cloud chamber or anything like that, because they don't interact electrically with the particles in the cloud chamber, but we detect them because of an interaction when they collide with something within the chamber that causes other particles to be emitted. So we detect the mass of the neutron when it interacts with another atom, and that's how they predict that a neutron is in transit. I agree with you that I don't believe that the neutron is existing as an individual component within an atom, but the energy of the neutron is there and released as a single neutral particle as it is in transit. So that's how we predict the neutron, from what I understand.
We don't see any neutrons coming out of any nuclear isotope.
Well, we don't see the neutron because it's not electrically interactive, but we see the impact of something massive striking another atom that causes another reaction. And that's how we predict that the neutron exists, because we can't detect it directly since it's only gravitationally or mass attractive, mass reactive.
We see charged particles. We can detect charged particles coming out.
Right, and that's right. That's why the neutron has to strike another atom to eject charged particles. It's those energy of those charged particles, the energy that those charged particles are released with, indicate that something massive struck that atom.
That's right. But if you look at the energy to 8 significant figures, it wasn't coming from a neutron.
Well, we don't know what it's coming from. We know it is coming from something that's massive and it's not electrically charged. So that's how we predict the existence of a neutron.
It's coming from something like a proton or some kind of charged particle. And
well, they do have things. They do have such things as neutron bombs, which eject neutrons and don't react electrically with things. They act physically when they collide with things.
Well,
I think my conclusion. This is Harry Ricker. My conclusion is that we can identify what a neutron is if it's a particle outside of an atom. But what happens is that inside of the atom, it's not possible to identify that as a separate unit that exists somehow inside the atom, which is what I interpret Bill as saying.
Yeah, well, that's exactly what Bill is saying. I interpret that too, and I agree with that fully. Matter of fact, I agree that we can't really detect even the existence of a proton or an electron within an atom. We can only detect outside the atom the characteristics of those charges. Masses.
We can make ionic and pionic atoms where the particle, the negatively charged particle that replaces an electron in an atom, it gets down to the lowest energy state, which is inside the nucleus. And so as it's making its transitions from one shell to another, and it gets inside the nucleus, we can see, first of all, the radius of the nucleus, and then we can see what type of interaction it's having with the particles in the nucleus. And so we're able to see that with multiple types of atoms. That was what I did my PhD thesis on. I used to be the world's expert on pionic atoms. Probably someone else is the expert.
Well, but Bill, we can't really see inside the atom. We can only see what energy we can only see what energy is coming out and going in to the nucleus of the atom. We cannot see the parts.
You know that from scattering that the particles, like the electron, form shells outside the nucleus. And we know that when you put a pion in place of the electron, it forms a shell. Okay.
But we only know about the interactive characteristics of the energy patterns that are within the atom. We do not know that those patterns contain a discrete particle anymore. We know that those patterns have probability waves, which say that this area, the probability of hitting something that repels or deflects a particle, which is also a pattern going into this, is predictable, but we do not know that it actually hit anything that's discrete. We just know about the interactions.
Well, when we plot the, there's a certain spectra that's given off when an electron is captured by an atom and it cascades down from one shell to another. There are patterns of the energy of the emission spectra that you see. And that tells you how the electron is interacting with the nucleus. But the electron never makes it into the nucleus because you don't see that effect. But when you use a much heavier particle like a pion, negative pion, it's 270 times the mass of an electron, and it makes it inside the nucleus before it even gets to its lowest energy state. And when it's doing that, as soon as it crosses the boundary into the nucleus, you see a change in the emission spectra from the type of spectra you were seeing when it was outside the nucleus. And what that is being affected by the interaction of the pion with the particles in the nucleus.
Right, but it all still comes down to what you're really detecting is the emission spectra. You're not seeing a collision of two discrete solid objects.
Oh yes, you are, because when the pion gets inside and it interacts with one of these, there's a nuclear reaction when it interacts, and the nucleus is split.
Yeah, and what it gives you is radiation patterns that you can detect that interact with electromagnetic fields in the gas chamber.
And
you detect the radiation.
You can detect all the particles that come out of that atom,
which are radiation patterns.
Well,
so again, it's not really something that's discrete.
You have protons and you have electrons, and those are the particles that come out.
Right, which are packets of energy.
Yeah. So anyway, what you're able to do is you're able to trigger with the cascade at a certain radius when this pion comes in, and kaon can do it, because it's even more massive than the pion, and you can even do it with muons, muonic atoms. So you've got a lot of different things you can do that you have to, and you collect all this data, and then you try to find a way to explain it. And so that's what I did, and I worked for what was called the Space Radiation Effects Laboratory, which is in Newport News, Virginia, and it was a NASA laboratory that College of William and Mary ran, and for 15 years it was the only laboratory in the world where you could do good experiments with pionic, kaonic, and muonic atoms. And
there are a lot of subjects that are being covered here, Bill. Yeah. And but really the question here, and what we're discussing here today, and I would like to bring us back, which is the nature of the atomic nucleus.
Right.
And so the main question is that whether anything that I've been explaining here strikes a chord and perhaps tries to answer some of these questions we had about, what is a neutron? How does it work inside the atom? Or is this all just pie in the sky and I'm crazy? I mean, it could be. So I'd like kind of want to get back to, whether we think that's the case rather than get too much into, say, accelerator physics.
Well, I think
we're talking science.
Well, why don't I just go ahead?
Science. We have to talk about the experimental facts.
Yes. Well, let me go ahead and finish off my little presentation here, and then I'm going to try and answer some of the questions that are in the chat, and try and answer some of the questions that Bill raised, and then I will open it up to open discussion. But let me get through the rest of my conclusion here, which is, like I said, I mean, the point is that is anything that I presented here start to make a little bit more sense than, say, the conventional model. And here, all I'm saying is that the protons are attached with something that we could call a neutron. And, in my model that I showed you, these white blocks represent what we recognize as a neutron. This is the thing that's contributing the mass of the neutron. But really, it's not a particle in the sense of a proton. All it is a positive and a negative charge, a positron and an electron. This would be consistent with like the data that Bill is saying that there's really no particle that has like the decay energy of these neutrons that we see in beams. I mean, these neutrons are created in beams, are created by collisions under special circumstances. And I didn't hear. I mean, it's news to me that for nuclei that spontaneously decay, that we cannot detect any neutrons coming out of them, because I think we can. I mean, we have neutron detectors. They detect the decay of the neutron. The neutron will stay for about 15 minutes. It's got that 15-minute half-life. And if neutrons are coming out of a source, we can detect those decays, and that's how we know the neutron's there. And so if you had a gigantic block of some radioactive substance, we could put neutron detectors around it, and we could conclusively say whether any neutrons are coming out of it. So, Bill, you're saying that, we've probably done that, and
No,
we know any neutrons coming out of it.
Franklin, we don't see any neutrons coming out of nuclear decay, but we do see other particles coming out of nuclear decay which cause the creation of neutrons in a secondary reaction. In other words,
secondary reaction.
Let's say a proton comes out or an alpha particle comes out of a decay, and it hits another nucleus, it can make neutrons. Okay, so in a nuclear bomb, that's how we get the neutrons. That's where they come from. But they're secondary particles. They're not primary decay particles. They're made by...
It's interesting that, the neutrons that we see in neutron beams and the neutrons we see coming out of these fission reactions may not actually have anything to do with the thing that's in the atom.
That's right. In other words, we know how to make them, but we don't get them by nuclear decay. We get them by a reaction, usually with a charged particle like a proton, and we bang it into something, and it makes all kinds of stuff. And then from that reaction, we get neutrons, and we have to get all the other particles because the neutron's neutral, although it does have a magnetic moment, so we can separate it to some extent from other particles that don't have a magnetic moment, and so that way we're able to.
Well, that would beg the question of, well, then what are those things that we were seeing in neutron beams? I mean, there's something. Now, I speculate that what those things are is that they really are very similar to the neutron we see in the atom. But if you can knock this thing free of an atom, it's just a positron-electron dipole, that has significant kinetic energy. That is what I am thinking these neutrons and the neutron beam are, is that they are just positron-electron dipoles with a lot of... And the thing is that with if you slow these things down, then I would say that they would actually cease to be neutrons, because you have to understand the rest of my theory, which says that actually all of space is actually filled with these things, right? All of space is filled with the positron-electron dipole. That would make the neutron exactly the same particle as the ether particle. The only difference is that this thing is be moving with high kinetic energy. And so if you ever slowed this thing down to stop moving, then it would just disappear. And I believe there is evidence of that happening, that they're saying like neutrons, when they measure the decay, there's some percentage that just flat out disappear, right? And it's in these experiments where they're trying to slow the neutron down as much as possible. So, my prediction would be if you took a neutron and you slowed it down, it would just melt into the ether. You would never see it. It would actually never have any chance to decay. And but that also brings up the question of, what in Earth is a neutron decay then?
Well, my understanding is that a neutron decays into a proton and electron. Is that not correct?
That is correct. A neutron decays into...
But you're saying it just dissolves into the ether.
No, what happens is that, these things, so let's say that this is a neutron. It's a positive and negative charge. And it's sitting in this sea of, practically identical particles, except it's heading at high speed, which means it can collide with another just stationary particle, right? So this is just a piece of the ether. It's also, structurally, it's exactly the same thing as what we observe as a neutron, except this is still, and this is moving at high speed. So it happens that because this has high energy, it can bind with another piece of the stationary ether. So it will collide. And this is why a neutron lasts so long, because it has to have a direct head-on, right, that special collision in order to get this binding to happen. So what happens is that it will bind together. So you get this object, checkerboard object, and it is not stable. So it falls into these two pieces. So this piece, what is this piece? This is two positrons and electron. What did I say that was? That's a proton. And then the a leftover piece is an electron. So when a neutron decays, it actually picks up more mass from the environment to build the proton and the electron. So this is why we see neutrons decay into protons and electrons. I mean, otherwise it would be hard to understand without it picking up additional mass from the environment, how a neutron could generate, two particles that ostensibly have more mass than you started with, or even more pieces than you started with. So that's kind of how I would say I would explain, what a neutron is outside of the atom, what's its relationship to neutrons inside the atom, why neutrons last so long, and why do they decay into a proton and an electron. So I think those are a lot of questions that are answered by fairly simple model that can be represented by just opposite charges.
Franklin, how do you explain the neutrino, a particular type of neutrino that's observed when a neutron decays to a proton and an electron?
Very good question. So as I said, I believe that all of space is basically filled with these positron electron particles. So what is a neutrino? So the way that I see a neutrino is that it is a specific type of electromagnetic wave. Kind of very similar to, say, a gamma ray, in that it's a very short pulse EM wave. But what happens is, since these basically quantize space. So if you have an atomic reaction, and that's the only time these neutrinos are generated, atomic reaction, it can do a very specific kick to another particle. So it's kind of like if you've got a Newton's cradle, you can see that, the ball comes down, the shock wave goes straight through the string of balls, and then it kicks the other ball out. That is the kind of energy wave that I believe a neutrino is. It would actually be kind of hard to tell the difference between, say, a neutrino and, say, a gamma wave. I think maybe the only difference really is the sharpness of the frequency. That neutrino is probably just like impossibly high frequency gamma wave, but fundamentally it's an electromagnetic wave. So that's how I see what a neutrino is, and that implies a couple things. For example, if that's the case, then there can actually only be one kind of neutrino, because there can really only be one kind of wave. But they think there are electron neutrinos, muon neutrinos, and tau neutrinos. What I think is happening there is that there are actually there aren't three different neutrinos, but there are actually three different ways in which neutrinos can be detected. It's just a matter of the energy range and your detection material and your experiment. So I believe that all this stuff about neutrinos having mass, that would be completely false, because an EM wave has no mass. This stuff about neutrino oscillations would also be wrong. They do not oscillate. It just depends on what kind of experimental apparatus you have. If you have apparatus which is sensitive to all three channels of neutrino detection, you see all of them, and that's what we actually see in the experiments. If your experiment is only sensitive to two kinds of neutrinos, then you come up with this conclusion that, there's a neutrino missing problem, but really there's no neutrinos missing. It's just that your experiment is incapable of detecting all three types of neutrino reactions. So that's my spin on what the relationship between a neutrino and a neutron is. So neutrino is really basically EM wave. A neutron really is a positron and electron. And it's similar inside the atom as in the stuff that we see as a beam. But the only way we can see neutrons outside of the atom is if it's moving with high kinetic energy. Because by definition, a neutron with no kinetic energy is just part of the ether, and it will just disappear. So that's how I see that whole universe of neutral particles. But a key part of my theory here is that only the electrostatic force exists. You know, the data that Bill Lucas points out, that there is no 1 over cubed or 1 over 5 power in the atom. If there were, you would see that in the energy budget of the atoms and the isotopes. We would clearly be able to see that.
Actually, if you look at the link that I posted, one of the ways of detecting a neutron is to slow it down.
Yes, you can slow it down. But if you slow it down enough, it will disappear. That would be my assertion.
Well, like I said, I posted the link. You can look at how they detect neutrons.
Okay. So in conclusion, you know, I'm asking, I'm making a big ask, which is that, you know, basically you abandon this planetary model of the atom. That in my model, if you didn't notice, that the electrons actually are bound inside of the, you know, the body of the atom. See, there's the electron, there's the electron. They're not floating around in a shell. They are bound inside of the solid atoms. And at the atom, the observed size of the atom is like, you know, the whole atom. I mean, there is no nucleus, or you could think of what we think of the nucleus is in fact the entire atom, and that it's big, right? But there's no strong force, there's no weak force, and that, you know, things like positrons and electrons do not annihilate. I mean, that is probably the hardest thing for people to swallow, because we've been taught from childbirth that positrons and electrons annihilate, and this totally makes this model impossible, right? And this is the reason why I believe this model has not been discovered, has not been considered, just because of that bias that positrons and electrons annihilate, right?
It's not a bias, it's an empirical fact. So, but anyway.
Well, what's an empirical fact? When we see a positron and electron come together, it produces gamma rays. That is the empirical fact. What is not the empirical fact is the conclusion that the positron and electron were destroyed. There's no empirical evidence to say that they're destroyed. You would have to go conduct a unique experiment to prove that. And I don't believe anyone has even tried to do that. I mean, you can prove that. There are ways that you can design experiments to show that, in fact, you know, there's really nothing left over. You know, but the experiment I've always suggested is that you do the positron electron reaction such that the resulting particle would have kinetic energy. Now, if I'm correct, then you should be that particle with high kinetic energy should be detectable. You can put it into like probably a neutron detector, a neutrino detector, and it will collide with stuff, and you will see the energy there.
But the energy ejected is equal to the amount equal to the mass that enters the electron and proton mass. The energy that's ejected is equivalent to that. The other issue with the model, the thing you might think about with your model too, is the mass deficit of those combined components is not explained. And also, if the model were that stable, then you have to explain why is there even a half-life, or why is there a nuclear decay?
Yep, so let's try and tackle, since we're into questions now. So the question is, what is the deal with mass? Okay, so we have, the biggest problem here is we have, you know, this is proton, right? This is electron. The mass difference is 1,836. But they're all saying, well, how can that be? This thing is only 3 times bigger than this thing, right? The question is, what is mass? So mass is the resistance of an object to its acceleration. That's what it is, right? Mass is not a measure of the quote-unquote stuff that a particle is made out of. It's only a measure of its resistance to acceleration. Now, I'm saying that, you know, space is basically filled with this sea of positive and negative charges. So to accelerate anything through this sea, it will take energy, because these things are a little bit sticky, and in order to get them to come apart so that something can pass through, requires energy. So first of all, this explains why energy is required to move anything in the universe, because in order to move something, you got to move something else out of the way, and that takes energy. Now the question is, how much energy does it take to move a single electron through this C? Okay, versus how much energy does it take to move this object, which is only 3 times larger in volume, through this C? And the interaction is not going to be strictly geometrical. The interaction is going to be between these charges. Because as I say, the most important thing about the positron electron is its charge radius. Because, you know, as far as physical size goes for an electron, I don't think we've actually found what the size is. It's so small, it still can't be measured how small the, you know, if it's solid, what its actual physical size is. So it's tiny, but like I said, it's its charge radius that's important. So like in this model here, the charge radius, which is important, is represented by the surface of these blocks. The physical size of the electron itself, you know, might be like the size of a grain of sand or something, you know, but it's charge radius, which is most important.
Franklin, I feel I have to interrupt you here. The big issue that I have with what you say is that you kind of explain why in response to a question, you kind of introduce another assumption into your theory that we hadn't heard about. So kind of what I would like is for you to list all your assumptions at some point so that we know what they are, and people can sort of address whether or not they agree with or don't agree with the assumptions. What you have is a theory that has a bunch of assumptions in it that as far as I could see, people aren't going to agree with. So right there, you have a problem. So, you know, if you could list your assumptions and then people could say, I agree or disagree with that assumption, that might be helpful to you because, you know, and I'm not even sure whether you accept Newtonian physics or not. Do you accept Newtonian physics?
Yes, I accept Newtonian physics. Newtonian physics.
Well, why are you accepting Newtonian physics? Reject a lot of other stuff. So, you know, I mean, the questions just multiply.
Well, that's science. So, and I'm trying to tell you, you know, the basis of my fundamental assumptions. So, like one of my fundamental assumptions is that space is filled with these things, right?
Well, and then your next assumption is that that the experimental facts that say those things can't exist are incorrect. So
yes,
right there, right at the get-go, your first fundamental assumption is contradicted by an experimental fact. And so you're assuming that the experimental facts are wrong. So, you know,
that's wrong. I mean,
that really kind of leads into this vicious circle.
I mean, that I believe that I have to lead you into believing that idea, which is that these particles disappear upon their collision, is wrong. Because
yeah, well, that's because the experimental facts demonstrate that. I guess the problem I have is I don't really see why we need an ether to begin with. So, you know, to get me to even consider your theory, you have to convince me that there's a need for an ether. And then after you know, I'm pretty skeptical about that. Then after that, you have to convince me that this ether is composed of a hypothetical particle that experimental facts show doesn't exist. And then, you know, I mean, the whole thing just, you know, leads me down a path that, you know, I find difficult to accept.
Well, I think the important thing for me to explain to you or try to convince you of is that the experiment of positron electron coming together empirically does not prove this particle disappears. Now, in order to do that, I have to just explain all the observed empirical results. Okay, now the main empirical result is that when we see positron electron come together, boom, they generate 2 back-to-back gammas. And then we do not observe any observable particle. Now, the gammas that come out have the energy according to E equals mc squared, with the mass being the mass of the positron electron. But the question is, why is that formula true? Why is it that E equals mc squared? Why not E equals 3mc squared, or E equals m times e to the 23rd, or any other equation? Why mc squared? And what's the speed of light doing in there, right? I mean, some people would like to say that's just an arbitrary constant, but it's not an arbitrary constant. The speed of light is something we physically measure. It's not, you couldn't have plugged in any other constant into that formula. So I have to explain, if I can explain to you where the gammas come from without destroying the original objects, then hopefully I'll be able to convince you that it is not an empirical result that these particles have to necessarily disappear. And this is how I explain it. I explain it as we have these two particles under the Coulomb force, and they will be attracted to each other. This we know for a fact. And as they get close enough, they will be accelerated to each other. And if you do the calculations for the Coulomb force, you will find that at a very small distance, the force is huge, enough to accelerate, theoretically, these particles to the speed of light. And I believe that's what they do. They get, as soon as they get close enough, and
that there's a need for an ether that is composed of these two particles which are incompatible with each other. So,
well, first I have to prove to you.
I have a real problem with that. But
I have to prove to you, first of all, that this annihilation doesn't happen.
You have to prove to me that an ether is necessary to begin with.
Yes, and then I can show you why the ether itself is necessary. But you're not.
I don't agree that an ether is necessary. So there's
that's right. And you're not going to agree because, first of all, you don't agree that a positron electron form the primary component of the ether, which I call a positive electron.
No, I say that there's no need for an ether to begin with, so I don't need to hypothesize what the components of it are.
Also, Franklin, I've given an example of how the transition occurs from the mass form to the pure energy form in the collisions of the electron and positron before, because as the electron and positron are accelerating towards each other, they are giving up their mass towards kinetic energy. In doing so, because it requires
formula.
But it requires the energy of their mass, the energy of their attraction to accelerate them towards each other. So as they accelerate towards each other, they are giving up their mass, and when they finally collide, their mass has totally turned into electromagnetic wave characteristics.
How?
Because they are, where does the acceleration energy come from if not from their own mass?
Now, if I accelerate my car, does it mean that it's losing mass? I don't think so.
No, because when you're accelerating a car, you're using gasoline to accelerate it. These particles, these electrons and protons, are using their very own electromagnetic energy to accelerate themselves towards each other. They're not getting the energy from the outside. You're saying this yourself, and that's correct. So they're attracting each other under the power of the energy with which they contain. You start with a full gas tank, and by the time you get to the center, you're out of gas and you have nothing but the electromagnetic energy left.
No, if you're out of gas, then you have two cars that are out of gas.
No, you don't have two cars. You just have the tanks. No container or anything. You have two tanks of gas. Without the tanks, you have the gas. You utilize the gas to generate the energy to accelerate
still
these.
Not at all explaining the
towards each other. When you're all done, all you have left is the energy, because you expended all your energy.
It does not explain what the speed of light is doing in that equation.
Because the speed of light is the maximum speed
at any constant.
The speed of light is the maximum speed at which it can accelerate, because that is the inertial characteristic of space. That's the permeability and permittivity of space prevents anything from moving faster than that. Any electromagnetics from moving faster than that. So that is the resistance.
I believe that
That's
that
the
is
resistance against which they're accelerating.
that is still doesn't explain what happens to the positron and what happens to the electron. See, now if you think it
Like I
annihilates,
said, you
this
start
has
with
to
two gas.
disappear.
You start with 2 gas tanks without the tank, and by the time you're done, the fuel is burned up, and all you have left is the energy that you expended, and that energy has been radiated out into space.
Now I think there's a major problem.
You're not starting with 2 solid cars and burning half the contents of that, half the mass of those cars. You're taking the mass of the 2 tanks, no tanks, or you can take the cars and you can burn the cars up too as part of the fuel to accelerate towards each other. By the time you're all done, those cars are totally burned up and there's nothing left but the energy.
Now this goes back to where I believe in Newtonian mechanics, which I do. Now if you do an analysis of this in Newtonian mechanics, you would find you'd have 2 particles heading at each other at the speed of light. Newtonian mechanics says this has got the energy of 1/2 mv squared. That's the kinetic energy formula. This particle has the energy 1/2 mv squared. Now, because they're heading.
Okay, let's do it with a solid fuel rocket without the container. Just burn the solid fuel.
Please don't interrupt. Please don't interrupt.
What was wrong with the energy?
When I'm trying to explain something. Please don't interrupt, okay?
Explain what I just explained to you and why it doesn't work.
Please don't interrupt. Let me complete my explanation. Then at least, then you can talk. But if you keep on interrupting me mid-sentence, I cannot explain this, okay?
I just explained what you're talking about doesn't make any sense.
What I'm talking about is
why you're talking about doesn't make any sense.
Pure Newtonian mechanics. You would agree that this particle heading at the speed of light has a kinetic energy of 1/2 mc squared. That's a physical fact, right? There's no way anyone can deny that. That is the kinetic energy of this particle heading at the speed of light. It's 1/2 mc squared. Same thing with this other particle. Newtonian mechanics demand that the energy of this particle is 1/2 mc squared.
Okay.
Now, what happens when these 2 things collide? Now, if they collide, and they can collide with an inelastic collision, like 2 lumps of clay crashing into each other, the law of the conservation of energy demands that the combined energy of these things, what's the combined energy of these things? 1/2 mv squared plus 1/2 mv squared is mc squared. The halves go away. Okay. It's 1/2 plus 1/2 equals mc. That is the net energy of these 2 particles colliding. And when they collide, they come together like your hands. And what did you hear when my hands collided? My hand had a specific kinetic energy. This hand has another specific kinetic energy. When they came together in an inelastic collision,
okay, disconnect your hands from the accelerating object and let's watch them accelerate towards each other on their own.
It doesn't matter.
Where did they get the energy to come together?
They get the energy from the Coulomb field. Now, I can explain where that comes from. But the thing is that I'm explaining that when my hands come together, they generate sound waves, which is a really similar phenomenon to gamma rays. Gamma rays are electromagnetic waves, just like sound waves are waves. And that is carrying away the energy of the collision. Okay, so that explains why we get 2 gamma rays and why they are at mc squared specifically, and it explicitly explains what the speed of light is doing in that equation, because they're just
simply have no m left. We started out with m when they were small and far apart, and because of their own acceleration towards each other, they're burning up the m. Take 2.
They are not burning up the m. That doesn't make any sense. How can they burn up the m?
Because you take 2 solid fuel rockets and you set them out in space and you ignite them each. Yes, it is going to lose the m. It's losing m to space. And
it's not going to lose.
That's how it becomes electromagnetic.
There's no way a particle can lose mass to. I mean, in fact, we know that when we accelerate particles, they gain mass. And that's another thing you have to explain.
That's an observation from the outside world.
Yes, it is an observation from the outside world.
They gain energy. They gain reactive energy. They have the energy of the particles that are exploding.
I mean, you have to deal with the fact that from a Newtonian standpoint, I mean, if you accept that the positron and electron are being accelerated to the speed of light, you have to explain the energy balance.
They're gaining mass because you're putting in an outside energy source to accelerate them. If they're accelerating under their own power, under their own Coulomb attraction, they are using that Coulomb attraction to obtain the acceleration that's needed for the collision. By the time they collide, the energy is all spent. It's just like taking two solid fuel rockets, igniting them, heading them towards each other. By the time they reach each other, they have spent all their energy and there's nothing left but the energy that's been expended. So when the collision occurs, you've already transferred all your energy to space.
And why does it transfer in the form of two gamma rays?
Because that's the way the two wave patterns interact as they accelerate towards each other. The gamma rays are being built as soon. The gamma rays are being built as soon as the objects start accelerating towards each other.
And how do they get
the gamma rays are maximized when they finally reach each other, and it's a nonlinear characteristic. The closer they get, the more exponentially energy growth of the gamma rays.
Yes, well, that's an interesting thought. You know, me personally, I just but I'm going to get back to Harry. So, Harry, I've explained to you where the observed gamma rays come from. It doesn't have to come from the destruction of the positron and the electron any more than when I clap my hands. You know, even though energy is coming out of that reaction, my hands are still here, right? So that's the thing I have to prove. I have to prove that the empirical result is not that my hands disappeared. The empirical result is that sound waves were generated or that gamma rays were generated, right? I have to, so Harry, have I in any way tried to pull you towards my side, join me, Harry, that the empirical result does not imply that the positron and electron were in fact destroyed, if I can explain where the gammas come from.
Well, I think Bill's already answered that issue in his previous comments about the spins not matching up and the other conservation.
Those are different issues. One issue at a time.
Like I said, I don't believe there's a need for an electron-positron ether in the first place. That pretty much. So, you know.
Well, let me give you this motivation.
I'd rather hear what Bill has to say about it, frankly.
The motivation between why you would need an ether.
Perhaps we can have.
Is the whole question of how is it that a positron can even affect an electron through so-called empty space? If there's absolutely nothing between a positron and electron, then how can they ever see each other? But yet they are attracted to each other to the point where they can be accelerated to the speed of light. And that's a lot of attractive force. But if there's nothing between these two, how can you even conceive of there being a force between it? There has to be something, like a field of something. There has to be something between these two particles to mediate a force between these two things so that they can see each other. Intuitively, we think that particles react only because they collide into each other. We can see that. You have proton, positron colliding into electron, they act like billiard balls. But if you have two billiard balls and there's nothing between them, and then we suddenly see them just spontaneously rolling towards each other, if there's nothing between or outside or around them, just pure empty space, how can that possibly happen? So I would say that
13 minutes left.
So motivation behind why an ether must exist. There must be something.
Hey, hello. Anybody hear me?
Yes.
Yeah, we can hear you, David. Welcome,
Hey,
David. You have.
Franklin. Well, listen, Franklin, first I want to say thank you so much for continuing to do this. I'm working outside doing a lot of stuff, and you guys, and I appreciate everybody here. It sounds like this discussions are going well, and it's not an easy thing to do, especially to take your time every week. And I do really, really appreciate that, Franklin. And it's not easy leading a group. Like they say, it's like herding cats, but I'd like to. I just want to say if I can have a few minutes at the end here you guys want to wrap this up and then speak to the group in general. That would be great if that's possible.
Okay, well, I'm going to try and answer a couple of the pertinent questions. So, I was getting to the, why is the mass different? And I have to get people away from this idea that mass is a quantity of particles. It's actually the interaction, the electrostatic interaction of the particle to its surroundings, which is a charge C. So,
right,
yes.
I think, just let me just make a sort of, because when we do our conferences, obviously we have to look into this. Why don't you, we have, 10 minutes. Why don't you take 5 minutes, wrap it up, just present. I think don't ask any rhetorical questions, just sort of, if I don't know where I'm sort of getting in here. And then when you're done, maybe then I can take a few minutes. But is that possible to do it that way? That way we don't get into the banter.
I'm trying to answer those critical questions. So that's mass, okay? So I have to get you away from this idea that mass is a quantity of things. That the one analogy that I put together is that if you have like a foam block and you're sticking it into like a plastic cube, you can easily stick that foam block into the cube. But now you take a second foam block, same size, you try and stuff the second block into that same cube. It's a lot harder. Then you take a third block and you try and stuff it into that cube, and it could potentially be 2,000 times harder to stuff that foam block in because it's a non-linear compression effect. And so with the proton containing 3 particles, if the compression effect is of the exponential range to the 7th, an increase in volume of 3 will increase the force by 1,000 times, right? So that's how I explain the mass differences between positron and electron. Now, Bill mentioned things about, spin. Does this explain spin? Well, spin is not really part of this model. Spin can exist or not exist because I'm only relying on the properties of positive and negative charges. Although I would personally say that spin as measured in Stern-Gerlach experiments done with silver ions is not measuring the property of the electron because you're measuring silver ions, for God's sakes. You're measuring the dipole property of a large atom. And so I actually don't believe that, me personally, that electrons actually have that property of spin. Now, Bill also mentioned things like magnetic forces. Now, the thing is that if you go look in Webb Elements, you can see like the magnetic resonance properties of atoms. And you will find that, for example, helium, which I am holding, perfectly symmetric, has 0 magnetic spin. But, if you start making bigger atoms so that they're lopsided, these are the things which have spin. Anything which is non-symmetric, because a magnetic field is able to grab hold of these non-symmetric pieces, those have gives the physical reason behind why things have these magnetic properties. Okay, although I would also personally say that individual electrons themselves don't have a concept of I forget exactly what you call it, a dipole or a resonance. That's only a property of large conglomerations of particles. And let's see here. What were the other questions here? And that there was a question of, what in the heck is a neutron star? What's a black hole? And the way I see that is that now the mainstream idea of what these white dwarfs are is that they're conglomerations of oxygen and carbon nuclei, and I would agree with that. They're just compressed conglomerations of those atoms. But If you compress it further, then you would find that the boundaries between the carbon and oxygen atoms disappear, in which case you just have one gigantic atomic nucleus. And I believe this is what they refer to as, they're calling it a neutron star. But you could easily call it, alpha star, because it's made out of alpha particles. This is just all compressed into one gigantic atom. So that is what I would consider alpha particles. Let's see, what other questions are? What keeps electrons and positrons apart? Now, that's a very interesting question. And that was, of course, one of my assumptions, as Harry points out. My assumption is that positrons and electrons are, in fact, solid particles. And as such, just like these two blocks, no matter how much they're attracted to each other, they occupy finite space. And as such, they can never merge, and they're just kept apart by their physical surfaces. Another aspect of my theory is that the subatomic world is a very violent, very chaotic environment. And so the environment itself will tend to, because there's so many collisions, will tend to drive everything apart, right? And so that alone will keep positive charges away from negative charges, because there's something that's constantly driving them apart. As soon as you drive them apart, they will come back together again, and they will at some point form some equilibrium, right? It's not like the positive electric charges stay here stately. I mean, they're being driven constantly apart and coming back together. So that's what keeps those particles apart. Yeah, I think I've answered the. Let's hear.
Please,
Sam says it's crazy time.
Now let David the Hillster do his talk, otherwise he doesn't get any time left.
Oh, we still got a few minutes.
Yeah, Franklin, I did say at 5 till you did have your 5 minutes. Is there a way we can wrap this up? I don't want to keep people too long here, anyways, because people start popping off. But yeah, I'd said 5 minutes, and it has been. Is it okay for you to wrap it up right now?
Well, I think I've answered most of the questions. If you guys have any other questions, very active on the email chain. So just ask me a question, and I love answering questions and challenging my theories. So go ahead, David.
Okay, well, again, Franklin, I want to thank you very much for doing this every Saturday, something I really can't get to. And believe it or not, this video conference is 10 years old. I started it back in 2008 with Dim Dim, of all things. We do have recordings from back then, so we do have like 200, almost arriving at 300 of these. And frankly, I do want to appreciate, it's a lot of commitment to be here pretty much almost every Saturday. And so thank you so much. I mean, I've heard good things about it, and that's great. What I want to mention, everybody, we are I'm going to be announcing very shortly, full swing, the CNPS conference, which is going to be in Connecticut this year, which is where where the MPA had its original, not original, but one of the places they were based out of for quite a long time because of Dr. Eberly Spencer. She was a mathematician at the University of Connecticut. So my goodness, I think there are more conferences held there at that university than any other place, and we have gotten away from that for a while, and I thought it would be really nice to have it back there in Connecticut. So if you're on the East Coast and you don't get to travel as much, and if you're close to Connecticut, it's going to be really well worth it. The conferences have been going really well. I plan to bring in somebody. I usually try to bring in some person now. We do have some donors that will allow that to happen. We do have our proceedings are open. Again, they're continue to grow. We use the share latex system, which is really good. We have lots of people to help on that. It's quite easy. You have a template. Yeah, it's a little bit of learning curve, but believe me, we've got people who are 80 years old learning it. My dad, who's actually one of the people who help out with that, he's 80 years old. So if he can do it, and he's an electrical engineer, everybody can do it. So that's really good. The other thing is too is we are obviously rebranding and doing some new things. One of the things that's becoming very successful is our YouTube channels. We now have 4 of us with YouTube channels, myself, my father. We have Jeff Yee, who has a really, if you haven't seen Jeff Yee's model, his ether model, it is quite good. It's a particle model. He actually does a model with the current particle model with quarks and even the pentaquarks in his system, and he's doing his YouTube channel. And we also have Nick Percival, who's been doing a channel. He's got quite a few videos up there. Giving you an idea how your work gets seen, I started in May of last year. It's not even a year. I have almost 30,000 views of my videos. I have almost approaching now 350 subscribers who watch my videos pretty regularly. The average video gets into the hundreds pretty quick, and my top video for my YouTube channel right now is over 3,000. I have one video called Special Relativity is Wrong. So the reason I'm saying this is not to push and tout anybody, but it is definitely what's happening as the YouTube channels are a way people will get their information. So if you've had it out there for 30 years, yes, I've tried everything. Well, this is a way to gather quite a lot of people. I'll give you an example. One other example for that is the Electric Universe is approaching in the next few days 100,000 subscribers. They have daily 17,000 views of their videos. This is through the YouTube. This is the way everybody gets their information now. I don't even watch network television anymore. I pretty much get all my information from people who I really agree with or I like their voice on YouTube. So please consider it. We've got another one coming on, which will be Glenn Borkert. He's an infinity guru. It's quite a good process. Check it out. I also rebranded our homepage. Go to naturalphilosophy.org, and that homepage is completely redone. The front page of it is. I'm going to be trying to reorganize a little bit better. I also made some sub pages. So, for instance, for the video conferences, these on Saturday now has its own little page there. I'm going to be talking to Franklin. We got to get back into making those events so that they appear on our homepage. It took me 10 minutes to get here because I had emails that were sent to me, but I expected to go to the homepage and find it there, and we do have the mechanisms involved. We want to do that. And as for the conference is going to be the end of June. So on the East Coast, we are going to be giving out some lifetime awards. So we're currently about to contact some of them. So if you haven't been contacted, it doesn't mean that you're not going to get a lifetime award. So that's something that we want to continue. And then the last thing I want to talk. For that, we do have another website we're still working on. This criticalthinkers.info. And its idea is to market this in a completely different way. I've ran this by lots of people. If you're interested in helping out with it, which we do need help, it is a fantastic place. In fact, it is very much like a very modern magazine type of thing where we look at, pretty much bullet points for people. We have literally problems in mainstream. We have people, like just profiles of people who are in the CNPS, and we have new theories and new models. If you have one of those, you want to be in this. It's just one of those things you want to do. But of course, Dave D. Hilster, who like many of us work 40-hour-a-week jobs and have everything else in our lives. I know we're all busy. If you do happen to be a person that can help out, it would be greatly appreciated, because we have really great things out there that we can't even get out, but that are sitting there. The last thing I do want to mention, and I'm going to talk with Franklin, and would like everyone's input, is I'd like to have one of these Saturdays when I can be here, because can't always be here, and for us to at least once a year to revisit what this Saturday morning videos are about, there's numbers of things that we need to know about it. Are we doing things that the people are here are liking? We need to get a sort of a more consensus on that. I'm not criticizing it in any way what Franklin's doing. He has been doing a great job. I've only heard good things about him from people, my spies that I have here, and I'm just kidding about that, of course. But also the real other thing, and I'm really wanting to do, and people's ideas on this, is to grow this forum. We have this service which we pay every year. We pay this service. We pay our service for a dedicated server for our web. We pay Share LaTeX is where you can write all of your stuff in LaTeX for publication. And we also, of course, we have MailChimp, and that's the list that you guys receive that Franklin's using. MailChimp has around 1,100 emails worldwide that we send out. So we are growing with our YouTube channels. We're growing. We have lots of people who aren't yet members of the CNPS, but are starting to be inclined to be that. So that's one of the reasons we're doing those YouTube channels, to attract more attention to our website and our work. I think we've got some really great marketing tools in the critical info, criticalthinkers.info. But what I'm looking to do now with this group is, what does this want to be, and how can we be attractive to people outside of our organization that we know would be perhaps interested in being here. There's two, I see this as two different things here. One is to keep our members and be able to have membership, talk to each other, get together, debate like you guys do. But I also think we need to, when a person comes in, if they've never been here before, unless they've been working really intensely on something, and unless they're really into natural philosophy, I think we need to somehow maybe once a month make a much more planned video conference on the Saturday morning, where we try to do more marketing on this side. So I am absolutely open. My door is completely open for what we need, what we can do with this. I would like to put together some ideas and then bounce them off people. Maybe even take half of one of these video conferences and make that, what should this be? Because I think growing this is really important, and all we have to do is maybe come up with a few things that are just more, some common sense things of how to do this. So again, I'm not coming here to try to hijack anything in any means. What I think is that it's not easy, again, because there's so many different opinions. But one of the things I'm finding, just to sort of wrap this up, and I think this is one of the ways we can help even our own conflicts, because we've been doing that at the real physical conferences, especially in the last 3 years. And I've been talking about it on my YouTube channel, is the idea of what Robert Distinti, who I'm trying to get here, he's a really great mind. If you don't know Robert Distinti, I've found him via Lori Gardee. He really talks about, and he coined this idea of polytheorism, meaning more than one theory explaining the same phenomenon. And one of the things I think we have to try to do amongst ourselves is understand that can happen, understand there are positives and negatives, understand that when we talk to each other about something, somebody may not get the idea that charge can't be just a plus and minus on something and it has to be a real physical thing. We're going to have to understand that people are not going to necessarily get more. We may get more about the person's theory than that person themselves. But what we really want to do, and I'm trying to do, I did one on the electric universe yesterday. I'm not a big electric universe person, but I praised them up and down because I said, we have to support each other. We have to look at ourselves that when someone comes to this forum, what we are doing is we're having really good debate, but we don't get too much into the arguments of the emotional side as much, and that we say, okay, I understand, I have to accept this about your model. And sometimes you're just saying to yourself, this guy is not addressing something that's fundamental, and this makes this all wrong. We have to at least have the attitude that we work together, that we can live in harmony with different theories for the exact same thing. Right now in class we have ether theories, we have particle model theories, we have action at a distance theories, we have lattice theories, we have more traditional theories like Bill Lucas has the force equations. So we really need to convey that. So my suggestion to everyone is to keep in mind at the very top level that when we go to conferences, I will help somebody with their theory, and I don't agree with it, but we need to have that camaraderie, because what will happen is somebody who's come in with their new ideas from outside, they're going to feel I've got to fight the mainstream, and now I got to fight the dissidents as well. So we're trying to change that into the idea that what makes any industry strong, what makes any group strong, what politics, science, engineering, software, is the strength of diversity, and that, you know, if one's going to come to the top eventually, it will, but it's not going to come to the top if we keep, you know, arguing amongst ourselves. That's one of the biggest criticisms we get. You guys have been very cooperative. I was listening in, and as much as you guys are fervent about things, you know, I understand. But again, that's my goal. I'm going to be sending out a newsletter to the same email list that, well, it is the CNPS's email list that Franklin has been using, and gratefully putting those out there. We will make sure this is to Franklin, we need to have this on our homepage. I have it up there right now, but it's probably gone because after the time it's gone, it's gone. But we need to make sure it's on our homepage. I couldn't get here, folks. I couldn't get here. So we need to look into that. So I will arrange with Franklin. I appreciate this time. That's why I came in the end here. I will arrange with Franklin for us to come up, and what I'd like to do is announce a all hands CNPS members meeting for me to give maybe a half an hour talk about the CNPS, where we are, and you know, get people's input on that, but also for us to I want all of you guys to think about what this form can be, what it is, what it can be. In my opinion, it serves many functions, and I don't think we need to necessarily cater to only one. We're not going to go all marketing and talk about things that only people who don't even, you know, aren't dissident scientists are going to come to. But we also can't keep ourselves into this little cloistered ball where, you know, not even our own members are sort of understanding what this is, and it's sort of like, if you like it and that kind of thing. So I'm going to do that, and I think at least twice a year I'd like to do that so that we get input from our members. And I really do see that we're growing. I mean, just to let you get a quick update, our paying membership has never been higher in the history of the MPA or the CNPS. No, it's not 1,000, not even 500. It's, you know, upwards paying members 100, active members almost 300. So it's quite good. We're financially stable. We do get, the only way we really get any money coming in for conferences to do special things, like bring maybe an Alexander Unziger from Germany to the conference, is we do get donations, and those are greatly appreciated as well. So the CNPS is in really good shape. We have marketing campaigns in the sense of what we're doing that really is attracting interest. People are knowing it. I've watched when I started my YouTube channel, the CNPS's YouTube channel had 120 some subscribers. I talk to it about it all the time. The subscription has already gone up 50 in the last few months of people who will watch these kinds of videos. We have these videos. I try to put them up there, but again, if you can help out with the organization, that's great, because I know there are people who don't have the time and they're going to concentrate on their work, and that's totally great. But if you happen to have some time and want to help out with the organization, that would be greatly appreciated. Bruce Nappi has been absolutely instrumental. The forums are just going great. So it's going well. The CNPS is going well. This is going very well. We just want to now sort of fit it into the bigger picture. Okay, so I really thank you guys for taking the time and being here every week. I do watch them because we try to put them onto the internet. So on the YouTube channel, please go to the YouTube channels, go there, because the more we have each person who subscribes to these, who listens to these things. Believe it or not, that's how it works. My curve for subscribers and viewerships is an exponential curve. It started out like this. It takes a long time, but now you can see it grow. They actually have statistics. Go to socialblade.com and you will be able to see my channel and the other people's channel and literally see the statistics of its growth. You know, I'm projected to have 1,000 subscribers by the growth rate that I have within a year. So you know, these are new audiences, and we get really great voices and new people. So, you know, get out there. I know people says, nothing's worked. Well, it is working. So thank you once again, and I will work on getting this updated with Franklin. Thank you so much, Franklin, for everything you do. It's super greatly appreciated. And I hope to see you here when we get our CNPS, what I would call town hall for the members. Thank you so much, guys.
All right. Thank you, David. And that will do it for this episode of the CNPS Saturday Science Chat. So if you guys got some topics, I believe next week will be an open week. If you want to beat me up on my theories, I would love it. But see you next time. Look out for the next message. Thank you.